All righty, good morning. Hey, Talia, how's it going?
It's going pretty good, thank you.
Good, good. So what can I do for you this morning?
I was wondering if I could talk to you about my honors project and also if I could go over exam 2 with you.
Sure. Let me get signed into my stuff here. How is the honors project going so far?
Well, I'm having a hard time connecting what I'm interested in, like specifically to the topics that we've learned.
Um, okay. There we go. We can get into the test. So you were working on Koshi last time we talked, right?
Pardon? What is that? Sorry.
Oh, so were you working on Koshi? Is that right?
I'm working on ultrasound.
Okay. Sorry, I'm getting you confused with somebody else. I'm sorry.
No
So,
problem.
what have you tried so far? I think kind of the first step is to come up with a question that you would like to answer or explore a little bit.
So basically, uh, I worked with my dad to set up, so we have like one circuit board with a oscillator, like an ultrasound oscillator, and then another with a microphone. And I was kind of like testing how the microphone can pick up the ultrasound waves and how like you can bounce it off of the surface. Like if you both point them at a wall, it bounces, or if you can also measure, like if you put an obstruction between them, then like it doesn't pick up. So since I'm interested in geophysical sensing, I was wondering like if I could sense different distances with that. So I'm working with my dad on that right now, and I was thinking of ways to relate that to this class. And I was thinking maybe with like the velocity function or something like that, or
I think you
like
probably
measuring the
could.
waves.
Yeah, I'm not too sure how distant. Let's see, range finding with ultrasound. I'm not too sure how it works, and you wouldn't have to get super granular with the math. Certainly we could try to cook up a basic model, but because when we're talking about ultrasound, we're talking about waves, the actual mathematics there is going to be a little bit more complicated than it would be if we're talking about a particle bouncing back. But maybe we could treat the wave front as a particle in one-dimensional motion. That might be an option, and we could describe sort of how we might do some range finding thinking about that. I just pulled up, let me turn on my screen share. Yeah, I'll turn my thing off. So I've just pulled up this paper, which ostensibly is about range finding, range estimation using coded ultrasound. And we might be able to, let's see, touchless human computer interfaces, augmented reality. We need the location we use as land site in real time can be accurate. Real-time locating systems, realize wireless positioning, sensors, distance estimates between reference points. Main practical difficulty. Let's see.
I mean, like this. I'm not sure if it would work to like put different sorts of like obstructions between like the two boards, and then to measure like the area underneath like a certain section of the graph to compare just like how the amplitude sort of changes.
Let me think about that for a minute. So maybe we can try to sketch something and see if we can't get a feel that way. I think that a good place to start regarding the mathematical content of your paper would be a sort of very basic rundown of how ultrasound works. This idea of sending out a sound wave, it hitting something, bouncing back. And maybe if I can start to understand a little bit what we're talking about with the range finding stuff, we can try to get a bit into the mathematics there. So you've got the device here, right? And it's going to send out some sound wave, yeah? And eventually this is going to hit some obstruction. and it's going to bounce and start coming back, right?
Yeah.
And then this device presumably also has like a receiver.
I have a receiver on like another device that's connected to it.
Okay. And this thing is going to arrive here, right?
Yeah.
Okay, so we hit the object, we bounce off, and we come back. And if we want to talk about finding the distance between these, that seems like it would be something to do with measuring the time it takes from this wavefront to leave the original device and come back to the receiver. Because the speed of sound is more or less constant. We can probably estimate the range that way. But we're also trying to get, I think the idea with ultrasound is to get like a picture, right? Like more information than just distance. So maybe just so I have an idea, what all information are we trying to get out of this? We want to get the distance to the obstruction, right?
I don't think I can get a picture of something with the equipment that I have, unfortunately.
Okay, that's okay. I'm just curious, what are we trying to get?
For me, like I'm the most interested, I guess personally, in trying to find the distance.
Okay.
And then possibly also finding like how the wave changes if you put different obstructions between it and the receiver, but I'm not sure like what specifically to focus on, like given the math topics that we've covered.
So I wouldn't stress too much. One thing about the honors project that maybe I haven't emphasized enough is that it actually, the math that you do in the paper doesn't have to be directly related to the math that we're doing in class.
Oh, really?
Yeah, yeah. It's neat if it is, but it's certainly not necessary. So we want to look at the changes to the wave based on the material of the obstruction or the shape of the obstruction. What are we thinking?
Probably material would be a little easier.
Okay.
But also, like, I don't have a very powerful oscillator, so I'm not sure if I could necessarily like go through anything too substantial.
That's okay. And it's not the case that you have to have a physical experiment to back up each of these things. We just kind of want to talk about the possibilities and how we might use some mathematics to help with this. So is it the case that the material would affect there are kind of two things we can measure, right? The frequency and the wavelength. And they're connected to each other. So is it the case that the material would have an effect on the wavelength or frequency of the wave that comes back to you?
Maybe like if the material kind of absorbs sound, it would be different than if it's like a material that would really reflect it well.
Yeah, okay, so amplitude, that's not something I was thinking about. So we can look at the material and see how does those two measurable quantities, how does this affect, right? No, affect. Yeah, the
Affect.
verb. Yeah, I always get those confused. How does this affect the amplitude and the frequency / wavelength? Amplitude, this might have to do with, like you said, sound absorbing. And that does seem to me like it would be a good step towards determining the material, right? At least a little bit the composition of the material. Is it soft, is it hard, right? A hard, non-porous object is going to reflect really well, whereas a soft or porous object would probably absorb some of that noise, that sound. The frequency or wavelength changes, I'm less sure about.
Yeah.
So I think you've got two things here that are more, any one of these I think would be enough to write a nice honors project. And I think the distance thing is something we can definitely do if we have the ability to measure time very precisely. And it's not something you need to be able to do physically, but in regards to distance, here we can use kinematics, right? We can use the basic laws of motion. We know that sound travels. I'm not sure what the speed of sound is exactly. I think it's somewhere around 600 miles an hour, but 343 meters per second. So let me just write that down, 343 meters per second. That's probably at sea level in dry air. And then in miles per hour, 761 miles per hour. So, so the velocity of the wavefront if we're just kind of thinking of this very first bit of the wave that comes out, right? The wave front, how fast that's traveling. That's going to be a constant. That should be, let's use SI units, the 343 meters per second. And we know that the distance would be, and we could whip out some of the math that we've been talking about here. This would be the integral of, well, let me say it a little differently. So the position S of t would be we can think of it as the indefinite integral of the velocity function, but the velocity function is constant. And if we think of that initial position as being 0, then this would just be 343 times t. Right, integrate a constant dt, and you just get that constant times t plus, all right, the plus c here. And we can say c equals 0 if we consider, if we call the position of the emitter his position, if we call that 0. So we start here at position 0, and we know we're going at 343 meters per second, and we're going to go there and back. So then the distance between the emitter, as long as the emitter and receiver are at the same place, the distance between the emitter and the obstruction would be half of the distance traveled there, right?
Right. Yes.
So therefore, if it takes, say, t0 seconds for the wave front to return to the device, then the distance from the device to the obstruction would be what? It would be half of the total distance traveled by the wave, right? So it's got to go there and it's got to come back. It's going at a constant velocity that whole time. So that would be 1/2 s of t0. All right, let me think about that. Is that correct? S of t0 would be the position, right? So distance 343 times t0.
So would it be 1/2 343t?
Yeah, I think that's it. Yeah, which would be, yeah, which is 1/2. Yeah. Okay, this is correct. 1/2 s of t0, which is 1/2 times 343 t0. So it takes t0 seconds for the wave to get there and back. It's going at a constant speed, and it's covering that distance twice. So the the rate times the time. That would be the total distance traveled by the wave, rate times time. And then you multiply by 1/2 because it's covering the distance between the emitter and the obstruction twice. So it's going to come down to how well we can measure time. That's going to be the thing. Can we say exactly when the wave leaves the device, and can we say exactly when the wave returns to the receiver? If we can measure time really accurately on those two things, like have a stopwatch that starts the second you turn on the emitter and stops the second the wave comes back, then we could get an accurate measure of that distance. And this is something that I think we could definitely make into a good part of the project. And you could try running an experiment. I don't know if the equipment you have has the ability to measure time like that or not, but even if it doesn't, we can still discuss this and maybe talk about how you could build that sort of thing in here pretty easily. I think just a fairly simple circuit, as long as the receiver and the emitter are close to each other. You just trip the circuit when you hit the button to turn on the emitter, and that circuit gets tripped again when the receiver first makes contact with the wave.
I think my dad just got like a really small sensor that will be able to tell that time. So I'll definitely try to do the experiment if I can. And if it doesn't work out, then I'll just discuss it like you said.
Yeah, I think that's a good plan. That's a good plan. And then the other question is material stuff, right? So what can we say? Can we measure the amplitude of the wave that comes back? And do we know the amplitude of the wave that goes out?
I might be able to. Also, like, should I just focus on one of those topics, or do I need to cover both?
Totally up to you. Totally up to you. I think
okay.
Either one would be fine for the paper. Especially if you're going to actually run an experiment, I think doing just one of them would be more than enough.
Okay, and then how in depth do I need to go? Like, is there a rubric somewhere that I can look at, or?
If I'm honest, I don't really have a set rubric for these because they vary so much. But what I can do is send you some old honors projects. So let me.
That would be great. Like, what do you grade them based off of?
So as long as I've only been doing the honors thing for a little while now, and I've never given anybody a bad grade on an honors project unless they just didn't do it. But let me send you some samples of like perfect score honors projects, and that should give you a bit of a point of reference.
And then I need to make a presentation. I need to write a paper and then create a poster. Is that correct?
The poster you only need to do if you intend to enter in the RU fair, but the paper and then the presentation based on the paper, those are the things that we need for sure.
Okay, great, thank you.
Looks like I don't have an email for you, so let me come over here. We'll just do this through Canvas. Oh, sorry, my wife's calling me. Give me 1 sec.
Yeah, of course.
Hey, baby, what's up? All right, sorry about that. Wife had some trouble at the dog park. Let me see here. So this is from last spring, and I definitely had a few really awesome honors projects. Interest. This one was okay. Yeah, this one was fine. Ray tracing one. I think this one was pretty good too.
So like what I'm seeing on these presentations is that it doesn't just focus on like the mathematics, also just like go into the history of the topic, go into the applications and such like that.
Yep. Yeah, you can talk about all sorts of different things. It doesn't have to be all just the mathematics. We just want to make sure that we address at least some of the mathematics.
Right.
What I've usually been telling people as sort of a guideline is that the bulk of the paper should be some sort of mathematical discussion, but it can, you can talk about, like this girl did laws of motion and how they showed up in like a Mortal Kombat video game. And she did some like frame measurements and tried to figure out if gravity in the Mortal Kombat universe is the same as gravity here. So I think, let's see. These, we got a few examples of, this was the same. This one, not super in depth. Yeah, okay, and here's a biographical one. So we've kind of got a feel for a bunch of different types of honors projects, and these all earned really strong grades.
Awesome. Thank you so much.
Yeah, no problem.
And then the last thing I wanted to talk to you about, sorry, were you gonna say something?
No, you're good. What's up?
I was looking back at my exam 2 grade, and I think you accidentally gave me a bunch of extra points.
Oh, well, it's very nice of you to let me know. Let's see. Sometimes I like, that's a little typo. Let's see. Oh, yeah, that's weird. I don't know why it keeps doing this. Canvas lately has been adding in these weird fudge points that I don't put in. I definitely appreciate you letting me know about that. Did those go away? No. Huh. Maybe if I explicitly enter a 0 and then say update. That works. Okay. Thank you for letting me know about that. Yeah, I don't know why Canvas has been doing that lately. It's a strange thing, but I appreciate your honesty there.
And then you mentioned if I do better on the final exam than I did on one of the tests, I can replace that score?
Yes, that's correct. So the final exam, if it's higher than your lowest midterm, we'll replace that midterm. So after everybody's taken the final, I'll go back and look at all the grades. And if your final exam score as a percentage, because the final is worth 150 points, but as a percentage, if it's higher than your lowest midterm, then I'll just replace that lowest midterm by the final.
And then besides from the Jello assignment, just want to double check if there's any other extra credit opportunities that I can do, like as supplemental work.
That's the only one, yeah.
That's the only, okay. So thank you.
Yeah, of course, of course. All right, then let's kick it over to Sarah. What's shaking?
Hi there, good morning. So I sent you an email with what I have so far for student teaching.
I think I saw that, but I haven't not had time to look at it yet. So here.
No worries. I figured it would just be so that you have it so that we can discuss it.
Yeah, all right, here we go.
And it's not complete yet. This is mostly just sort of an overrunning script. And what I'm thinking of doing is that I'll make some condensed notes in PowerPoint form and record myself talking over them.
That sounds good. That sounds good. My only warning with PowerPoints, be very careful to control the pacing. It can be really easy to like go super, what feels like a reasonable pace for a PowerPoint is different than what's a reasonable pace for someone taking notes. So I would like in your head, just count to like 10 or something every time you like get the itch to flip to the next slide and make sure that you're giving enough time for someone who's handwriting it to write it down. But I don't think that would be any problem.
Sounds good. And then there's bits here, so yeah.
I like the way that you're describing this. So the bottom line, instead of, you can think of the x-axis as the curve y = 0, right?
Yeah.
We're changing that, and we can look at one of these individual rectangles and see, okay, that the height is f minus g. That's good. And this is the correct definition for sure. Sounds good. Visually inspecting of the rectangle. Yeah, this is fine. We might want to remind people, so xi star and gi star, like the star there doesn't mean anything special. They're just using that for the name of the sample point because they're assuming that you could use left endpoints, right endpoints, or midpoints.
Okay.
While we're getting into this, we might just want to tell people, don't worry about the star. The star doesn't really mean anything special.
I was actually wondering about that. It was one of my questions for you.
Yeah, because they don't want to, when they write down this Riemann sum, they don't want to say this is a left endpoint Riemann sum, or this is a right endpoint sum, or a midpoint sum. They want to just say it's any one of those. And so they use the star to say, well, these xi's could be different for a left or right endpoint. If you wanted
but the Riemann sum they gave us is,
that would be fine too.
Okay, I might do that because the Riemann sum they gave us is for right.
Yeah, and I think the right endpoint sum is the one that we're most familiar with. It's the easiest one to work with.
Okay, so I'll stick to that one.
Lowest calculation. Could be the xi calculated the same way here. Yeah. Okay, yep. So the xi's here would be calculated the same way as they are normally.
Okay.
It's a plus I delta x, and delta x is the same also, b minus a over n.
Okay, and a, what's the a come from again? Remind me.
Oh, they're just using a for the area. So
For the bounds. Okay. So I'm like trying to think of if that would change at all if it's got two equations, but no, the bounds will still be just one bound.
So capital A is the area of the region S, so the total blue area, and then little a is the lower bound, big B is the upper bound. So if we're asking about the capital A here, that's the total area of the region.
Okay.
And
I've
then,
been sort of swapping in A and S since it's the area of region, right? S.
So by S, they mean the region, and by A, they mean the size of the region.
Oh.
That's all.
It's very textbook of them.
It is, yeah. It's a small finicky thing. If you wanted to just refer to that region as A throughout, you could do that.
Okay.
But it's up to you. No harm either way. Okay, and then we've got some examples. Good. So we'll find the intersection points. Those will be our bounds. Good. Sketch the curves. Yeah, nothing wrong with showing people with Desmos, but definitely we want to make sure that we can sketch these by hand. That's not too hard.
I mostly just did this to avoid sketching it out and then scanning a messy sketch. I got you. Do lovely straight lines.
Yeah, nothing wrong with that. Nothing wrong with that. Let's see, and I think there's nothing wrong with finding these y values, but I don't think we actually need them. So it's up to you whether you want to include that. Could be useful for the purpose of drawing the picture. But the bounds that we're going to use, the -3 and 3, just come from the x values. And we might want to remind people that these bounds of integration will almost always be the x values of the intersection points.
The reason why I included it is because there's a little bit later on, and this is something I was going to ask if it should be included or not. They do one where it's flipped, where you're using where your bounds are horizontal instead of vertical.
Yeah, and in those cases where we're integrating with respect to y, we would be concerned about the y values only.
Okay.
Sorry, my wife just got home. Let me brief her a little bit on the baby situation.
No worries.
All right. So, when somebody using rectangles, vertical parallel axis with delta x, dx for the integral, good. And limits of the x values, good. Solve the integral, simplifying integral, good.
And I have a note for myself on the side. This is where it starts getting a bit incomplete.
Okay, no worries.
I just wasn't able to finish typing.
So for this guy, this is good, right? And we just need to evaluate between the bounds.
Yeah.
Good, but yeah, this is fine. This is fine. So the only thing we would need to do to finish this example is plug in the bounds. We could, one quick thought, we could make use of a symmetry argument here. And it's up to you whether you want to introduce that. But if you notice the area to the left of the y-axis, the area from
Is
-3
equal.
to 0, is the same as the area to the right of the y-axis, the area from 0 to 3. So you
Okay.
could argue that the function you're integrating here, 6 minus 2x squared after simplifying, that this is an even function. And if you wanted to save time, you could say this is equal to twice the integral from 0 to 3. And that would make the evaluation step at the end here just a little bit simpler. But there's no need to do that. You don't have to do that. But when in order to finish up this example, we do need to evaluate this between the bounds. That's the only thing that I would say we still need to do there. And then if we're laying out a procedure, yeah, sketch the graphs and find the points of intersection. And then I would say that we want to figure out whether we're going to integrate with respect to X or with respect to Y.
Okay. That was one step that I honestly did not understand very much.
So let's see. Yeah, let me show you a couple quick examples here, and hopefully we can get that to a place where you feel comfy. Those are the problems that people end up struggling with a little more than the others. So let me switch over.
Yeah, I just couldn't figure out what the relevance of doing that was.
Well, some curves you cannot express as a function of X, but you can only express as a function of Y.
The ones that are like Y squared or Y is stuck underneath something.
Right. Yeah.
So we just
if I take
do we
X equals Y squared minus 1. That looks like this. And
Okay.
maybe I also have the curve Y equals 1 minus X, which looks, I'll put it in a different color. That looks like this. If I wanted to find the area bounded between those curves, because the first one is not really expressible as a function of X, it fails the vertical line test. I wanted to find the area of this region here. Sort of the intuition for all the stuff that we've looked at so far is you integrate the upper function minus the lower function. If we're working with respect to Y,
it'll be right minus left.
Right. If one or both curves are functions of Y, we integrate also from like Y equals A to Y equals B, the right minus the left dy. And you could make a similar Riemann sum argument if you wanted, like thinking of a little Riemann rectangle in here. So the length width of this rectangle would be the right minus the left, and then that thickness would be a little delta y thickness.
Okay.
So here we would have to find those intersection points. One of them is clearly 0, 1. But if we're hunting for the others, we would take this guy and solve him for x. So this would mean x is equal to 1 minus y. And so I would set these guys equal to each other. Y squared minus 1 equals 1 minus y. And I haven't planned this ahead, so this might be these might be kind of nasty numbers. But what do we get? We get y squared plus y minus 2 equals 0. And well, that might factor nicely, right? Plus 2 minus 1. Yeah.
Yeah.
All right, what were the odds? So one of them is y equals 1, and that's the one up here that we already found. The other one is y equals -2. So this guy down here, I don't know what the x value is, but I know the y value is -2. And truth be told, I don't particularly care what that x value is.
Okay.
So I would integrate here from -2 to +1, my right function as a function of y, which is 1 minus y, minus my left function as a function of y, which is y squared minus 1 dy. And I like this example because the first curve is given x equals a function of y. The second curve is given y equals a function of x. And when we realize that because that first curve is only expressible as a function of y, we have to think of the other one as a function of y as well. So this like solving for x here, and then okay, I can say like this is like g of y, and this is like f of y. So then we're integrating f of y minus g of y dy. And from there, it should be pretty straightforward, right? We just combine like terms, take our antiderivative, normal FTC2 stuff. And I think doing one example like this is a really good idea, even if you just wanted to do this one. That way they've seen at least one problem where we're setting up with respect to x and one problem where we're setting up with respect to y.
Okay, sounds good.
Cool. All right, then. So yeah, so the curve sideways, we do the right minus left thing, corresponding values on the y-axis instead of the x-axis. Good. Previously used to calculate change, vertical change instead, vice versa. Yep. Okay. And
That's
then,
where I'm gonna put
if you have curves that trade place multiple times, we would need to split it up.
Yeah. So should I do a specific example for this? To be honest, I found this really straightforward, but if you understand the above, you will definitely be able to do this.
I think it's a matter of taste. So if you're going to present this as the integral of the absolute value of the difference, then I think it would probably be worthwhile to run through a specific example.
Okay.
If you're going to present it like, okay, we'll just calculate each one of these separately, then I think you could probably get away without doing an example. But I think there will be time to run through an example.
Okay.
So maybe one example where the curves do change places at least once would be good.
Okay, sounds good.
Sine and cosine are really good like this. I think if you take sine and cosine from like 0 to pi or something, 0 to pi over 2, that's like a classic example.
Yeah, I'm pretty sure there's even like one in the book that I can
yeah, I think
reference.
So.
I find it so hard to. Oh, sorry.
No, go ahead.
I also find it really hard to understand what the textbook is saying. Like, I could even understand the material, having learned it in class, and I'll go back to the textbook and still have no idea what it's on about.
Mathematical writing is incredibly terse. I think this book isn't the worst of those, but the thing that I've been told and I kind of like is that you read math with a paper and pencil. So as we go through here, and we want to understand just from the book, I think writing each thing down and like stopping to work the examples on our own is really helpful.
Okay.
But yeah, I agree. Mathematical writing is challenging to read, and it's its own thing. Like learning how to read math is very different than learning how to read literature or something like that. Some of these examples are a little bit out of control. Like this one, I don't think anybody would really want to do this by hand. Yeah, similarly here, we're doing some approximation stuff. I wouldn't stress about that. I think a little bit the discussion of this would be good. Like where you ended in your notes is fine. And then the thing is you just explain that, yeah, the absolute value of f minus g is either f minus g if f is the upper and g is the lower, or g minus f if g is the upper and f is the lower. So like in S1, we would do f minus g. In S2, we would do g minus f. And then in S3, we would do f minus g again. And that idea of thinking upper minus lower, that always works. And usually that's how I present it. I don't usually even give this discussion of the absolute value thing.
Okay.
And then, yeah, here, the sine and cosine example would be a fine one to do. So we can go from 0 to pi over 2, and we see cosine's the upper from 0 to pi over 4. So we do cosine minus sine there. And then sine is the upper from pi over 4 to pi over 2. So we do sine minus cosine there. And I think that will be enough for people to get the idea. So as long as we have one simple example of upper minus lower, one simple example of upper minus lower where they change places like the sine cosine, and then one example of right minus left if you wanted to do this one or the one that we did. Either of those I think would be fine.
Sounds good.
Cool.
I'm
Is there
thinking of
anything else I can yeah, go ahead.
So I'm thinking of doing like the standard and then doing the right minus left and then doing the one with the two different curves.
That's
Like the two,
good.
like the upper and lower. Okay.
Yeah, you want to do like a standard upper lower, a standard right left, and then an upper lower where they change places. That would be fine.
Yes. Yeah. Okay. Sounds good. And then I had 2 other questions. One's really quick. I requested a homework extension because I didn't realize that homework assignment was due Monday. So I've already placed the request. So I had spent that Sunday working on this actually.
Okay.
And
Yeah,
completely
no
forgot
problem.
that
Here,
would be.
let me get in there. If you
It's just the
requested
last
it before
section.
yesterday afternoon, it should have been cleared already. But if it was yesterday afternoon or later, then I probably still need to clear it. So let me take a look.
Oh, no, it was probably literally yesterday afternoon.
Okay. Yeah.
And I just had the last section of it to complete.
Sure.
Oh, there it is.
All right. Let's push that to Monday.
Okay. Thank you.
Yeah. Yeah. No problem. What was the other thing?
The other thing, I had sent you, I don't know if you have time for this right now, but I had sent you a fresh copy of my final paper with some stuff added to it.
I don't think I have time to go through that right now, but I should be able to take a look at it this afternoon and get you some feedback back through email. And if there's something that we want to talk about through Zoom like this, then we can do that maybe, I guess Thursday's the holiday, so maybe early next week.
Okay, sounds good.
Cool.
I just want to make sure I don't leave out anything that should be in there.
No,
and
yeah,
then,
I trust that you're being thorough, but let me go ahead and save a copy here just to find it real quick.
And then other than that, as far as my presentation, what does the presentation need to contain?
I think usually what people do for the presentation is basically just run through their paper. And then if there's anything that you can demo or anything like media that you would want to show, like a little video or something like that, you can include that in the presentation. But it's basically just you discussing the paper. The content of the paper should be the content of the presentation, plus any sort of multimedia or something you wanted to do.
Okay.
Let me see. I'm not sure I've gotten the fresh copy of the paper here. I don't see anything else with an attachment. So maybe I could ask you to resend that.
Yeah, let me double check if I sent it via Canvas or Outlook.
Okay. Yeah, Canvas stuff I should get here also, but maybe I didn't get an attachment. Sometimes attachments from Canvas don't make it through to my inbox there.
It also might be attached to a discussion about my final paper. That email, it might be attached to that.
Okay, let's see.
Like it might be a response. I'm not certain though.
See if it's not too much of a hassle. Oh, here we go. So here's this one. This one's from October 21st. That's probably the old one, right?
Yeah, this one's from November 14th. I'm resending it. Give me a sec there. Forward.
Yeah, it's weird. I don't see it here.
All right, sounds good.
Alrighty. Yeah, I'll take a look at that, and if there's anything in there that feels like we still need to add or clarify or anything, I'll let you know. But just based on what I saw before, I suspect that you're in good shape.
Oh, okay. Sounds good.
Cool. Alrighty then. I'm gonna run. I gotta go ahead and prep some other stuff, and I will see you tomorrow.
Okay, sounds good. Thank you so much.
Of course. Take care, Sarah.
You too. Bye.